sklearn neural network MLP classifier. Description: the MLP classifier is a feed-forward artificial neural network and that uses backpropagation for training. It is used for classification tasks where the target variable is categorical. It consists of multiple layers of interconnected nodes, each layer performing a specific computation on the input data. Inputs: X a 2D array of shape n samples. N features representing the input features for training or prediction. Each row corresponds to a sample and each column corresponds to a feature. Y a 1D array of shape n samples, representing the target variable for training. Each element in the array represents the class label of the corresponding sample in X. Outputs: YPRED a 1D array of shape n samples, representing the predicted class labels for the input samples. Probabilities a 2D array of shape n samples. N classes representing the probabilities of each class for each sample. Steps: initialization: the network is initialized with random weights and biases. Forward propagation: the input data is passed through the network, with each layer performing a weighted sum of its inputs and applying an activation function. Backpropagation: the error between the predicted output and the actual target is calculated and propagated backwards through the network, updating the weights and biases to minimize the error. Training: the network is trained by iterating over the training data multiple times epochs, adjusting the weights and biases until a desired level of accuracy is achieved. Prediction: once trained, the network can be used to predict class labels for new input data. Metrics: accuracy: the proportion of correctly classified samples. Precision: the proportion of correctly classified positive samples among all samples predicted as positive. Recall: the proportion of correctly classified positive samples among all actual positive samples. F1 score: the harmonic mean of precision and recall. Loss: a measure of the error between the predicted output and the actual target. Visualization plots: loss curve: a plot showing the evolution of the loss function over epochs during training. Confusion matrix: a table showing the number of samples classified correctly and incorrectly for each class. ROC curve: a plot showing the trade-off between true positive rate and false positive rate for different classification thresholds. Fine-tune parameters: hidden layer sizes: the number of nodes in each hidden layer. Activation: the activation function used in each layer. Common options include ReLU, tonnage, and logistic. Solver: the optimization algorithm used for training. Options include LBFGS, SGD, and ADAM. Alpha: the L2 regularization parameter. Learning rate: the learning rate used in the optimization algorithm. Maxiter: the maximum number of iterations for training. Toll: the tolerance for the optimization algorithm. Uncertainty methods: confidence scores: the probabilities of each class for each sample can be used to estimate a uncertainty in the prediction. Monte Carlo dropout: a technique that uses dropout during prediction to generate multiple predictions, which can be used to estimate the uncertainty. Challenges and fixes. Challenge 1: overfitting: the model may perform very well on the training data but poorly on unseen data. Sample use case that resulted in Challenge 1: training an MLP classifier on a small dataset with a large number of features, leading to a complex model that memorizes the training data. Fixes to Challenge 1: reduce the model complexity by decreasing the number of hidden layers or nodes. Use regularization techniques such as L1 or L2 regularization to penalize complex models. Use dropout to randomly drop out neurons during training to prevent overfitting. Increase the size of the training dataset. Challenge 2. Underfitting. The model may not be able to learn the underlying patterns in the data, resulting in poor performance on both training and test data. Sample use case that resulted in challenge 2: training an MLP classifier with a small number of hidden layers or nodes, leading to a model that is too simple to capture the complexity of the data. Fixes to challenge 2. Increase the model complexity by increasing the number of hidden layers or nodes. Try different activation functions. Use a different optimization algorithm. Adjust the learning rate. Challenge 3. Vanishing gradients. The gradients may become very small during backpropagation, preventing the model from learning effectively. Sample use case that resulted in challenge 3: using deep networks with sigmoid activation functions, leading to very small gradients due to the saturation of the sigmoid function. Fixes to challenge 3. Use activation functions like ReLU that do not saturate as easily. Use batch normalization to rescale the activations and prevent gradients from vanishing. Use gradient clipping to prevent gradients from becoming too large. Challenge 4. Slow training. The training process may take a long time, especially for large datasets or complex models. Sample use case that resulted in challenge 4: training an MLP classifier with a large number of hidden layers or nodes on a large dataset. Fixes to challenge 4. Use a faster optimization algorithm like ADAM. Use smaller batch sizes for training. Use a GPU to accelerate training. Challenge 5. Difficulty in selecting hyperparameters. There are many hyperparameters that need to be tuned to obtain optimal performance. Sample use case that resulted in challenge 5: choosing the optimal number of hidden layers and nodes. Activation function, optimization algorithm, learning rate, and other hyperparameters. Fixes to challenge 5. Use grid search or random search to explore different hyperparameter combinations. Use early stopping to prevent overfitting. Use cross-validation to evaluate the performance of different hyperparameter combinations.